Section 3.4, the chain rule. Here's where we observe how composite functions can be differentiated. So if we have a composite function like capital F of x, which is made up of two functions, lowercase f of lowercase g of x, then the derivative of capital F of x is first the derivative of the outside function, lowercase f, evaluated at g of x again, and then we multiply that by the derivative of the inside function, so the derivative of g of x. So for example, find capital F prime of x if capital F of x is equal to the square root of x squared plus 1. We can identify the function that is inside the square root function as g of x, which is x squared plus 1. That's the thing that is inside the square root, so we're going to call that g of x. That means that there has to be an outside function, which we would label lowercase f of x. That function is just the square root function, meaning you put in an input and then take the square root of that. So we're going to call lowercase f of x the square root of x. We're going to need some derivatives to move forward. So first with lowercase f of x, we're going to rewrite that using a power like we've seen before, which then means that the derivative uses the power rule. So f prime of x would be taking the original power 1/2, that becomes a coefficient, and then we subtract 1 from the previous power, so 1/2 minus 1 gives us negative 1/2. And then we are also going to need the derivative of g of x, which is, again, just going to use the power rule. So if g of x is x squared plus 1, then g prime of x, its derivative is 2x. So then putting this all together, the derivative of capital F of x is first the derivative of lowercase f evaluated at g of x, and then we multiply that by the derivative of g of x. So this becomes 1/2, and it would be x to the negative 1/2, but we are putting g of x in for x now. So that becomes x squared plus 1 to the negative 1/2. And then we multiply that by g prime of x, which is 2x. Since all that we have here is multiplication, the 1/2 is going to multiply by the 2, and so then all we're going to be left with is just the x squared plus 1 to the negative 1/2 times x. And since we do have a negative power, we might as well just rewrite this as a fraction. So we'll have the square root of x squared plus 1 in the denominator. That's what happened to the x squared plus 1 to the negative 1/2. And then that x that we had, that becomes our numerator. And that's it. The other example that we looked at was in this next one. Differentiate part A, y equals sine of x squared, and then part B, y equals sine squared of x. So here this is playing around with the idea of inside and outside function, and we are going to get two completely different answers from this. So first of all, in part A, the function that is inside is the x squared. It's pretty easy to see because x squared is inside some parentheses. So that means that we would want to take the derivative of the outside function first. The outside function is the sine function, and the derivative of the sine function is the cosine function. And then we have to evaluate that at what was originally inside the sine function. And then we multiply by the derivative with respect to x of x squared, which again is just going to be 2x. So this means that we have cosine of x squared times 2x. And the way that we would want to write that to organize it would be to bring the 2x up to the front and then cosine of x squared after. Part B, y equals sine squared x, we need to remember that what that really means notationally is that we are taking sine of x first, and then we are squaring that. So here the inside function is the sine function. the outside function is the squaring function, which is a power function. So first we're going to use the power rule. And the power rule would say, take our power of 2, that drops down to be a coefficient, and then we subtract 1 from that power, so 2 minus 1 is 1. And then our base, sine x, is what was inside before. It stays inside in this derivative. But what we have to do before we finish is now multiply by the derivative with respect to x of the sine function. So this becomes 2. This is just sine x, because sine x to the first is just sine x. And then times the derivative with respect to x of sine x is cosine x. And so this is just simply 2 sine x cosine x. Definitely two different answers. Differentiate y equal e to the 3x. We did this in a previous lesson using the product rule. Now we're just going to use the chain rule. So first of all, the outside function in this case would be the exponential function, e to the x. And if we remember, if we have f of x equal e to the x, then the derivative is the same thing. So really, the first part of this derivative is just exactly what we started with, e to the 3x. But then we have to multiply by the derivative of the inside function. The inside function in this case is 3x. And the derivative of 3x is just 3. And then again, we can clean this up. This gives us 3e to the 3x. From those last couple of examples, we actually can start making some generalizations. First of all, if we think of y as a function of u, and then what's inside there, u, if we think of that as a function of x, then we can say y is equal to f of u, and u is equal to g of x. Then by the chain rule that we've been writing down, the derivative of y with respect to x, so dy dx, is first the derivative of y with respect to u, and then we multiply the derivative of u with respect to x. So for example, in what we saw above, if we let y equal sine of u and u equal x squared, then the derivative of y with respect to x we saw was cosine u times du dx, which just turned into cosine of x squared times 2x. And we can do that for the other trig functions that we've had and a lot of the other functions that we've seen so far, like we just saw with the exponential function. E to the u in that case was e to the 3x, so e to the u and u is equal to 3x. And then we can also do this with a power of a function, like we also saw above. If y is equal to g of x raised to the nth power, then we can say that f of u is equal to just u to the n, and then u is equal to g of x. And then we get dy dx is equal to, by the power rule, n times u to the n minus 1 times g prime of x, which is the same thing as writing n times g of x to the n minus 1 times g prime of x. All of these generalizations here are exemplified in those three examples that we just finished above. So now let's just do a few more. Find the derivative of capital F of x, which is equal to 1 plus x squared to the 99th power. To understand why we're looking at the chain rule, just think if you had to do this from a previous rule, you'd have to use the product rule, which would be 99 copies of 1 plus x squared. So we don't obviously want to do that. So by the chain rule, and from the generalizations that we just saw above, I can use what's written right here. In this case, n is the power 99. G of x is 1 plus x squared. and then I have to subtract 1 from the power, so 99 minus 1, and then I need to multiply by the derivative with respect to x of g of x, in this case 1 plus x squared. And this turns into 99 times 1 plus x squared to the 98th, and then times 1 plus 2x. The derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x. And there really isn't much that we can do with this. If you were thinking maybe we could simplify, that would involve multiplying all of this out, and we definitely don't want to do that. So we're going to leave it just like that. All right, another example, also related to those generalizations we did above. This time, find the derivative of f of theta equal to tan squared of n theta. So here we have to think, we're changing up what the variable is. The independent variable this time is theta, not x. So we're taking the derivative with respect to theta. So then f prime of theta, again, it might help if we remind ourselves that the notation tan squared of n theta means tangent of n theta raised to the second power. So the first thing that we would have in our derivative would be the power rule. That 2 drops down as a coefficient. Our base tangent of n theta is then raised to the 2 minus 1 power. And then we need to take the derivative with respect to theta of tangent of n theta. Now you might notice here, this derivative that I just wrote down, that also involves a composite function. Tangent of n theta means that we have n times theta inside the tangent function. So we're going to need the chain rule again. So just cleaning up what we have so far, first of all, 2 tan of n theta, that's what was left over. Now times the derivative of what I have underlined there. The derivative of the tangent function is secant squared. And then I have to evaluate that at what was inside the function to begin with, n theta. And then I need to multiply by the derivative with respect to theta of n theta. And just think of this like a number times x. If you were trying to find the derivative of a number times x, it's just the number. This is the same thing. X is just now being played by theta, and the number is just being played by the constant n. So the derivative that we have left to do to finish this, the derivative with respect to theta of n theta, is just n. So this turns into 2 tangent of n theta secant squared of n theta times n. And the only thing that we could do to clean this up is, since n is a constant, we could say 2n tangent n theta secant squared n theta. So you can see now we are starting to compound upon a whole bunch of functions that we've seen before, and we can start imagining that a lot of possibilities are out there. So for example, in this next one, capital F of t is equal to 3t minus 1, parentheses, raised to the 4th power, and then that's being multiplied by 2t plus 1, which is being raised to the negative 3 power. So we see here we've got a product, and we've also got functions inside of other functions. So now we're getting combinations of a couple rules that we've seen. So first of all, capital F prime of t, I'd have to find, by the product rule, the derivative with respect to t of our first part in the product, 3t minus 1 to the 4th. And then after I've finished with that derivative, I multiply that by 2t plus 1 raised to the negative 3. And then the other part of the product rule is take the derivative of the second part of the product. So the derivative with respect to t of 2t plus 1 raised to the negative 3 power. And then multiply that by our first function, 3t minus 1 raised to the fourth. And now we're just going to use the power rule with these functions, just like you saw up above with a couple of the other examples. So first, the derivative with respect to t of 3t minus 1 raised to the fourth would be 4 times 3t minus 1 raised to the 4 minus 1, which is 3. And then we need to multiply by the derivative of what was inside. So the derivative of 3t minus 1 with respect to t is 3, just the slope of that linear function. And then with the rest of what we have, the derivative with respect to t of 2t plus 1 to the negative 3 power. Again, that power, negative 3, would drop down. And then I would have 2t plus 1 raised to the negative 4, because negative 3 minus 1 is negative 4. And then multiply by the derivative of 2t plus 1, which is 2. And then that's being multiplied by 3t minus 1 raised to the fourth. And if we wanted to try to clean this up a little bit, maybe we could just simplify all of these grouping symbols. So before the plus, I could say 4 times 3 is 12, and then 3t minus 1 to the third, 2t plus 1 to the negative 3. And then with the second part, negative 3 times 2 is a negative 6, and then 3t minus 1 to the fourth times 2t plus 1 to the negative 4. And maybe there could be some other things that we could do, but I think that's enough. Now that we have this chain rule pretty well established, we're going to use it to answer an open question we had from a couple sections ago. We never really figured out what was the derivative of any exponential function. We only did this for e to the x. So now in this example, we want to differentiate y equal a to the x. And the first thing that we're going to do is we are going to rewrite a to the x in this way. By the properties of the exponential function and the natural logarithm function, we can rewrite the number a as e to the natural log a. And then a to the x becomes e to the natural log a in parentheses raised to the x power. By properties of logarithms, this turns into e to the natural log of a times x. So we can see that the whole exponent is just natural log of a times x. So then we want to differentiate a to the x. So this is just the same thing as the derivative with respect to x of that new notation. And we can see that we're taking the derivative of an exponential function, but inside we have a constant times x. This is exactly like what we had in the previous example, e to the 3x. So then this turns into the the exponential function, just as it is, just like we had e to the 3x before. Now it's e to the natural log a times x. And then we need the derivative of what's inside the exponential function with respect to x. Which is just a constant times x. So that means the derivative is just the constant natural log a. Which is what we have there. And then we can just simplify this because e to the natural log a, we already said was a before. So the first part of what I have written there is just a to the x. So now what we see is that the derivative of a to the x, any exponential function, is just a to the x times the natural log of a. So whatever the base is, it's the base to the x power times the natural log of that base. And here you can see this works for base e, because the natural log of e is just 1. The derivative of e to the x is just e to the x times 1, or e to the x. All right, and then finally, one last example. Similar to a previous one, just the multiple use of chain rule, we can start to see that all of these rules start to compound, and we get many different variations of what has to happen. So this is where we want to be familiar with these rules pretty well so that we can understand what to do. So if I want to differentiate f of x equal to sine of cosine of tangent x, we want to think that we want to work our way outside in. So first I have the derivative of the function that is way out on the outside, the sine function. That's cosine. And then I have to evaluate that at what was inside the sine function, cosine of tangent x. But then I have to take the derivative of what was inside the sine function. So now I move inside the next level. And now the derivative of what's outside now is the derivative of cosine, which is negative sine, evaluated at what was inside the cosine function to begin with. And then I have to take the derivative of the function that was next inside, in this case tangent x. And then putting this all together, cosine of tangent x times, this is negative sine of tangent x, and then the derivative with respect to x of tangent x is secant squared x. And there really isn't much to do at this point to simplify, except maybe we could bring the negative out to the front and just reduce the number of parentheses we have. So we could say negative cosine of tangent x, and then that's times sine of tangent x, and then that's times secant squared x. Since we have trig functions inside of trig functions, there's no identities that we can use to simplify, and that's it.